Welcome back. Today we're going to be looking at getting information from a graph and looking at domain, range, inputs, outputs, all the stuff we've been doing but on graphs. So let's get started. We'll start with our creed. Like always, remember it's cool to say, it's not cool to not say. It's cool to pass, it's not cool to not pass. Today's a new day. I can read and remember well. I can develop my viewpoint and apply it correctly. I have eyes to see, ears to hear, and a mind to understand. It might not be easy, but it's worth it. All right, let's go. Let's get started with getting information from graphs of functions. So, let's see. It's going to start off really easy, then it's going to get a little more complicated, and then it's going to be really nice at the end when we cut out whole problems. So, starting off super duper easy. One thing I've been really stressing lately is to read this in good words, not just saying T of 1. And that's what we've always learned. And anybody can look at this graph. If you've been in 9th grade or 10th grade algebra from a long time ago, you can look at this graph and say T of 1 is 25. Boom. That is a correct answer. But what we're trying to do now is asking ourselves, if we zoom in super big, and we don't look at the graph, we don't look at the conditions, we don't know anything about temperature, what we want to ask ourselves is, what does T of 1 mean? Or what does T parentheses 1 mean for us? And what it means, if we start back at section 2.1 and we just work our way through this function, it says if I have an input of 1, ... what is my output? So it's asking yourself that big question, saying a function is a thing that takes some set of numbers or some number, runs it through some system, and then spits out some other number or some other thing. So what this is saying is, if I take 1 and run it through this thing called T, what do I get? Or what is T of 1? And that's what we're really looking at. I know for the super easy ones like this, it doesn't matter so much. But once it gets a little more complicated, it's going to be good to look at it in that way. So let's do this one with, yellow's a bad color. Let's do red. What about T of 3? We're going to go over to 3 and look at it and say, what if I plug 3 into this red line? See that long red line? If I plug 3 into that line, that's something. What spits out, or what is my output of that function? It looks like 30. So we'll say T of 3 is 30, and then we'll fly just because I know you know what you're doing. T of 5 looks something like 20. Color coded nice for you. There you go. Let's ask ourselves the question, which one's larger? We'll do this in orange. T of 2 or T of 4? Which number is larger if we're looking at these two things not as functions but as numbers? These are numbers that we're given when plugging an input of 2 in, and a number that we're receiving when plugging an input of 4 in. So we go to 4, and we go to 2, and we say 2 looks like it's approximately, if you zoom in real big there, it kind of looks like, I don't know, maybe 34 or something. So we'll say 2, T of 2, it's 34-ish. And T of 4 looks like it's right on money. Could be a little off, but T of 4 looks like it's pretty much right at 25. So which one's bigger? T of 2. We don't even need to know exactly what it is to look at that graph and know that it's bigger. All right, so we're looking at, for what values of x is T of x 25? Again, if we zoom in real big to this, we say forget about the graph, forget about the function, forget about anything that we knew from the problem. Let's look at this and say, what is this saying? What is this in words? Can you read this as? And it reads as T of x equals 25. Well, that doesn't mean anything, so let's take it back a step and look at it as a function. If T is a function, then we input some number, we don't know the number, but some number x gets put into T, and some other number is given to us. So some number x will give us 25. So what we've got to look at is not where's 25, but what number x will give us 25. So I'm going to go up here in this, I'll do it in green. Say look right here at 25. I'm just going to look all the way across. Oh, looks like I hit it twice. Looks like we hit it right at, here's dotted line going down, 1 and 4. So it looks like we've got T of 1 is 25 and T of 4 is 25. Another way you can write that is the set of numbers. Draw that set notation. 1, 4. Cool? All right. Find the values of x where t of x is greater than or equal to 25. Again, if we zoom in really big, what's that saying? Saying we plug in some numbers. Some of them are going to give us a number bigger than 25. Where would those be? Well, I think we just took care of it. We got to look at this red line and say, is this bigger or smaller than 25 on the left there? Right there where I'm turning it yellow. Looks smaller because it's a less number. It's underneath it on the y-axis. Same thing on the other side. So really what we're doing is on this blue area right here, we're sandwiching that function in between 1 and 4. So it looks like for which values of x is it greater than? Every single number in between 1 and 4, right? So 1 through 4. That's not a good way to write an answer. So we're going to take it and we're going to put our x inside of 1 and 4. And then we're going to ask ourselves, does it include 1 and include 4 or not include 1? Well, it says for which values is t of x greater than or equal to 25? So then we'll include it because that or equal to. Another way you can write that, if we're breaking it down in set theory, if you want to rewrite that, you write a set, x bar, and then rewrite it. If you want to write it in interval notation, we'll do hard brackets or the squared off brackets and go 1 through 4, including 1 and including 4. If we did the soft brackets or the parentheses, then it wouldn't include 1 and it wouldn't include 4. Last but not least, this net change we talked about in an earlier video. That stands for total change in y, or total change, not in x, but in y. So the net change we're looking for, and we remember that formula of f of, well, I'll write f of b minus f of a. But actually in this case we're working with t, so I'm going to rewrite it t of b minus t of a. And then it's up to us to define which one is b and which one's a. Usually we're going to go left to right, A to B, just like reading a book. So now we're looking at t of 3 minus t of 1, which we did in the very first section. Looks like t of 3, if we're going back to part A to look for it. Part A, we already defined those, so we don't have to redo it. We're looking at 30 minus 25. Looks about 5. 5's not a great answer, though, because 5 what? 5 cookies, 5 t-shirts. T stands for temperature, so 5 degrees Fahrenheit. And we are good to go. It's pretty cold. All right? Last thing I want to really teach and touch on is this domain and range idea. It's this idea of when we look at a graph, that's the easiest way to find, to me, that's the easiest way to find domain and range. So we can look at this figure right real quick, but what I'd rather do is go back to that example 1 and see if we can identify the domain and range. Cool? So if we look at this figure for 1 second, we see the domain is down there on the x-axis, right? And the question that we like to ask ourselves for domain is, what can x be? In this case, what can x be? It's all the things that that red line touches on the x, right? So x could be this all the way to this. It couldn't be past it on the right, and it couldn't be past it on the left. So that's our domain. I'll label it. Domain, the question we ask ourselves is, what could x be? Now range, a lot of times students will like to jump the gun and say, what can y be? But we want to define it a little more specifically than that. The range, I like to define, if you're going to define it in words to talk to each other about it, the range is what does that make y? Not what can y be. And what's the that there? Well, the that is the domain we just defined. So the domain always comes first, which goes back to day 1 of this class when we talked about functions. Saying a function is something that takes a set of numbers, funnels it through a system, funnels it through some equation, and then spits out another set of numbers. So it's important to not just think of domain and range as two distinct things, but as a domain is what can x be on this graph, and a range is what does that make y. If I only look at those x's, what's my y? Not just what are all the y's. If I look at those range of x's, what is the range of y values? Okay? So let's try this on example 1 just to kind of see. So domain, I'm going to scroll up. Even though it's not on the worksheet, I think it's a good way to do it. Erase all that and you can look at it a little better. All right, so domain. What can x be? Let's just start at 0 and ask ourselves up. Can x be 0? Yeah, looks like 15. Can x be 1? Yeah, looks like 25. Well, let's cut the difference. Can x be 0.5? Yeah, looks like 20. Well, if we cut it again, could x be 0.25? Yeah, and we'll start to see slowly that x could be all of these numbers. Every single number in the world almost, right? And for the sake of this problem, I'm going to go ahead and draw this arrow, and we're just going to pretend like it goes forever that way. And it comes back to some temperature. It looks like 15. So we'll just pretend like it's homeostasis, like it's coming back to 15 happily, and it's going to stay there. Cool? So what can x be? Well, it starts at 0, right? We just saw it starts at 0, and it kind of keeps going all the way until it goes on forever. So in bracket notation, we write 0, comma, infinity, soft bracket. And then in set builder notation, we write x bar, x has to be greater than 0. And that's it. Because x has to be greater than 0. Oh, or equal to. Good catch. X has to be greater than or equal to 0. And the only way we know to define that is we go back and look at our graph and say, can x be 0? Can our x be 0? Well, let's think about it in terms of temperature. At time 0, what was the temperature? 15? Yeah, time can be 0 then. All right, now let's look at what does that make our range. So what does this make our range? If we look at 0, our lowest y value at 0 is 15, it looks like. And then it climbs all the way to about 34. And then it starts to go back down, but it never really gets back to 15. So we go from 15 all the way up to 34-ish before we start to come back down. So based on that red line and based on those x's, we go from 15 degrees all the way to, what do we say? Just to be consistent, 34. What did we say in the last problem? We said 34. Cool. All the way to 34 and then back down. Awesome. We'll do one more and then I'll let you try the rest, or you can look on the notes once they're completed to try the rest as well, just so you get some good practice. Let's see. Let's do one that has 3 parts like this. Solve the given equation or inequality graphically. So here we have 2 different equations on 2 different sides of the equal signs, right? We've got one that looks like it might be a quadratic and one that looks like it might be a line. So I'm going to go ahead and do this, underline this blue and underline this red so that you can see which one we're working with at which time. I'm going to call this one f of x and call this one g of x for no reason, just because I want to. You could call it y and t. You could call it a and b. Don't call it x because you already have an x used. You call it whatever you want. y1, y2, some people like to do. All right, so let's draw a table. And I'm going to start defining x's and y's. Oop, I'll call it f of x. Whatever you called it. I'm going to start defining some x's and y's. Now, I personally like to just start at -3 and work my way up, but you are welcome. You pick whatever numbers you want to pick. You can pick negative a billion. You can pick 4. I picked -2, -1, 0, 1, 2, and then I added 3 because you're going to see something cool happen at 3. But as you expand and you really want to see this graph, you'll see what if you want to add or take away some numbers. So once we plug those in, you trust me on that. Just trust me that I did this beforehand. You can plug numbers in. If you want to practice plugging numbers in, let me know. We can practice plugging numbers in, but that's not what this lesson is. So you're just going to have to trust me that I'm going to fly through the arithmetic here. And we're going to skip it and just say that's our XY graph or table. So we got another X, G of X table where I'm going to pick the exact same numbers. I think the first time I did this problem, I stopped at 2. And then when I started to draw the line, I was like, oh, look what's about to happen at 3. So I went ahead and added 3 to the table. And I'm glad I did because it was a nice, easy number. And you'll see something really cool happen in a second. 11, 16, 21. So there are my tables. And now I'm going to graph and see what happens. So here's my blue graph. A little note, you can do this anytime you want to do it. I gave you a table with 1, 2, 3, 4. Often you're just going to add a 0 there, 10, 20, 30, 40. Because it turned out to be a pretty big function. So, if you see what I did there, I just changed the numbers. I didn't change the x's. I just changed the y's. That's totally okay. So, -2, 11, boop. -1, 5, right there. 0, 3. 1 comma 5, looking like a parabola, looking like exactly what it's supposed to be, a parabola intersecting the y-axis at 3. And then 2 comma 11, that went back up faster. And then 3 comma, oh, it didn't go back up faster. I added an extra number on this side. 3 comma 21. So it looks like a parabola. And if you were to guess what negative 3 is, you'd probably hit the nail on the head. That'd be negative 321. I didn't add it to my table, but we're pretty good. All right, here we go. Let's graph the next one. Negative 2 comma 4. Negative 1 comma 1. 0 comma 6. Ooh, looks like we crossed the line, didn't we? Wait. Negative 2 should be negative 4. I am bad at math, but good at not messing up for the video. So we got negative 2, negative 4, negative 1 comma 1. Let me check my math on that one to make sure. Negative 1. Yep, that's right. All right, then we're good to go. 0 comma 6. 2 comma 16. 3 comma 21. And so on. All right. So here we go. We're going to draw that line. Not a perfect line. I might have messed up a little bit, but that's okay. All right. So now what we're going to do is we're going to look at this table, and we're going to say, okay, well, oh, I think we're almost done, aren't we? Sweet. So we're going to ask ourselves, where does it look like it intersects? It looks like it intersects right there. So this function looks like it intersects right there. And like we said in this class, we're going to try to use nice, neat numbers. So if you draw this green line, probably we're looking at 1/2, right? And it's on the left side, so that's a negative 1/2. So let's find out and see. If we plug in that negative 1/2 into our, let's do our, which function? Blue function first. So if we do f of negative 1/2, we end up with something like 2 times negative 1/2 squared plus 3. If you don't see what I'm doing, I'm taking that guess. It's a guess about where the intersect is and plugging it into our original function. So we get something like, remember PEMDAS says do parentheses first and exponents. So we're going to leave that 2 alone. We're going to take care of this 1/2 by turning it into a positive 1/4, because negative 1/2 times negative 1/2 is positive 1/4. And then we can do our multiplication where we end up with 1/2 plus 3. And if you like fractions, you can say 7/2. And if you don't like fractions, you can say 3.5. Let's check with our red function. So now we've got our g of 1/2, negative 1/2. And our g of negative 1/2, the function is 5 times negative 1/2 plus 6. Let's see what happens. 5 times negative 1/2. We're going to cut it in half and say we're going to go negative. I'm great at math. 2.5 plus 6 looks perfect. What's negative 2.5 plus 6 looking like? Subtract 2 from 6, subtract another 1/2. We're looking at negative, positive 3.5, which is exactly what we got. So that was a good guess to go with a nice easy guess of 1/2. Generally on a test, if you're struggling and you think you did it perfect, but you didn't get a nice neat number, it'll be half of a nice neat number, which would probably be in the 1/2 area. All right, let me show you what to do on the next 2 sections, and then we'll call it a day. So let me see if I can copy this all. That way we don't have to redraw it. Boop. Headed down there. Intersection was at like 3, right? Something like that. That'll have to do. All right. So now what we're looking for is, well, where is our blue function less than or equal to our red function? Where does that blue line reside underneath the red line? Well, it's actually pretty easy to do, because we can just look at, if we look at the left side of each of those intersections, the blue line's greater than. So that's not it. If we look at the right side, the blue line's above. The blue line is above the red line, so that's not it. So the only good chunk we can look at is that middle section, right? And we already found those numbers because we just did that in the last section. So it's looking like we don't even need to do a whole lot of math. We know it's going to be either in the middle or on the outsides. And because the blue's on the bottom in the middle and less than means underneath, we can go ahead and say this middle green highlighted section is what we're looking at. And that looks like it travels from negative 1/2 to 3. Right? X is going from negative 1/2 all the way to 3. And does it include it? Let's just look back at the problem. Underlined, yes, it includes it. Another way you can write that is X bar, and then we're going to start at negative 1/2, less than or equal to X, less than or equal to 3. Good to go. So you can probably envision what the next thing is going to look like, right? If you think back to earlier when we flip the sign around, it just changes the opposite meaning, all it means. So you flip that sign around, we got an opposite meaning. We literally don't even have to do any math. We can just say, hey, instead of those green sections, now we're taking the yellow sections. Whoops. Forget I did that. So instead of those green sections, we're going to look at the yellow sections. So we're going to start at negative infinity and start working our way up until we hit the first special point or a point of intersection, right? So if we start at negative infinity, we use one of those soft brackets. So we start at negative infinity, soft bracket, work our way all the way up till we hit negative 1/2. And do we include it or not include it this time? Looking back at the problem, I'll circle it. We do not include it. So we're going to soft bracket that thing. And then we're going to join it together, or union, that's what the U stands for, is unite two things, with the next yellow section, which starts at 3, not inclusive, and goes all the way to infinity. If you want to do in set notation, you can do X bar, and we can say that X is less than negative 1/2, and X is greater than 3. Those are the two sections that we're allowed to use for X. Everybody good with that? Okay. So that's the way to do the less than and the inequalities, the less thans, the greater thans, the equal tos. I will make a quick note. Oh, I need to look at this real quick. Real briefly, we're going to look at increasing and decreasing, which should be one of the easiest things we do today and honestly all year. Increasing means that the y value or the function value or the f of x is increasing in value or in number as the x increases, right? So if you look at this green section, I'm highlighting it green, that is the increasing section. And you can use rules of domains like we just did to determine that. I'll go ahead and give you a little hint. It's probably going to be from 0 to 20. And then this blue section right here, you notice nothing changes, right? There's a word for nothing changing in math. It's a constant. So that's a constant value or a constant section. It's the constant function. And it's the function that says no matter what the time is in that blue section, the function is 150. So that would be our constant section. And that goes from about 20. Looks like 20. It could be a little more than 20. Maybe even 25. Let's say 25. 25 to 35. Could be a little off. That's okay. I guess that would change the green one to 25 too. Okay, let's look at one decreasing function and call it a day. Look over here at this decreasing. The one section where it goes back down, that's our decreasing section. So our decreasing section of the function looks like it goes from 40 all the way to 50. There'll be better grid lines if you're ever working on it through a test or something. But that's the idea of increasing and decreasing. And what that means in real mathy terms, if you didn't have a graph to look at, it would say that as x is getting bigger, f of x is getting bigger. As f gets bigger, f of x gets bigger. That would be an increasing function, right? And then likewise, as x gets bigger on a decreasing function, f of x better be getting smaller. So that's the idea of increasing, decreasing. It's not too crazy. It kind of goes along with that net change idea. If the net change is positive, that means it went from a... If the net change is positive, it's increasing. If the net change is negative, probably decreasing. All right. I'm going to go ahead and give you a pass on this last ones. The ones that look super calculatory. I'm just saying pass. You can look at the notes and see we don't have to do those. We'll learn about them later and ways to do it, but with way less tough numbers because of the calculator section of things. But if you do want to do those, I can make a separate video for learning's sake, and we can practice using a calculator, not for the test and not to use on the test, but for the learning of the pre-cal and the algebra behind it. So that's it for today. Thank you for watching. I'll see you soon. See you in class. Don't forget to watch any videos that you may need from college algebra back in the day. Don't forget to study for tests. Don't forget to look at the lecture notes. Don't forget to look at the suggested homeworks. Lots of different resources for you to learn to know what you know what you don't know, and know how to learn what you don't know. Have a good day, and I'll see you soon.